First of all, just a PSA, never get your matrices wet and never feed them after midnight. Okay, so, all right, so, good. We're getting to finding null space and column space. As I said, 3 ways to find column space, 1 true way to find null space. You need to know all those other 3 ways. They have different values and methods and yeah. Okay, what is the plan? All right, so this is a little piece in here before we get to finding those subspaces where we introduce a couple of incredibly important things. And the first is that we're going to take row reduction, which we know how to do, and we've already done this once in class. We've gotten a little as sort of an appetizer, but the plan is we're going to take ax equals b, and we were going to ux equals c, right? We're doing this triangle thing, but we're going to do the complete row reduction, which we did when we found, say, inverses, if we could. We're going to generalize, we're going to have a better understanding of pivots. We're not going to be worried if there's a pivot missing. It's just, that's fine. We are going to, instead of reducing to u, the thing we're going to get to this r, and I like to use this sub a. That's very important. That will matter later on. So this is the reduced row echelon form of a. RREFs, not like ROUSs, but REFs. Reduced row echelon form. So it's row reduction, and the echelon means staircase. Yes, awesome. We will introduce pivot and free variables. Again, something we've touched on. Huge. Got to get this stuff right. And absolutely essential, really, really basic thing about a matrix is its rank. And, well, we'll see what this is. But basically, it's the number of independent rows or the number of independent columns. It turns out they're the same thing. That's not obvious that they will be, but kind of have to be. And we'll do this to start with a matrix I like to call Fezzik. All right, so this is Fezzik. It's a 3x4, or he, I suppose, is a 3x4. And it's French, 3x4. That's going to allow us to investigate some of the complications that arise with rectangular matrices. So instead of solving x equals b for a specific b, we will, at this point, look at just a general b. Okay. So what is x? I want you to think what x would be. X is, what dimension is x? Right, so x is, this means that x is in R4, right? It's 4-dimensional, 4 columns. So x1 times this column, x2 times this one, x3 times this one, x4 times this one, some arrangement of those has to equal b. All right, good. So this is just a little setup, and then we'll use in the next piece where we get to, but I need to introduce reduced row echelon form, pivot and free variables, and the rank. That's what we're going to do here. So it's a little bit of row reduction, which is always good for us. So we set up the usual thing, right? So the usual thing. So it's just going to be A, that nice big juicy line there, ax equals b, boom, boom. So just stick them in, 4, 4, 12. So what can you see about those first 2 columns? Something very naughty is happening there. They are the same, well, they are the same in that they point in the same direction. Second one is a multiple of the first one. So this is our, right, so that's clearly some redundancy there. We could just get rid of the first column, it wouldn't matter, right? So we'll see how that plays out. So this is good, so we're going to do our row reduction. We could put elimination matrices and all these things, but I'm just going to write down row reduction. So we know, hopefully we know at this point that we can do 2 steps. We can do the first, we're going to get rid of this one and this one to start with, and we can do them at the same time because they just use row 1. So, all right, so row 2 prime, always use the same thing, right? It's 1 times row 2 minus something times row 1. Row 3 prime, same structure. what is that? Row 3 prime. It's 1 times row 3 minus, do not be cavalier. There is one true path, the monks have told us. So we're trying to get rid of a 2. So we get rid of a 2. We're dividing by the first pivot. It is sitting there, D1. D1. And then we're trying to get rid of a 6. So 6 divided by 2, again, D1. Right. We could call them multipliers, but we're sort of moving beyond that because we're awesomeness incarnate. Okay, so, all right, we're getting carried away. So the first row stays the same. Very important to be able to do this well. So B1. Okay, now we're going to handle these B1s and B2s floating around, yeah? So it's really just the second row minus the first row, so 0. If you look at this, it's going to be a 0 here, 0 here, 6 minus 3, 10 minus 4, and so on. Right, so 0, 0, 3, 6. Now we have B2 minus B1. So the point of having a general B is that later on we can stick in whatever we want, right? So, and play around with it a bit, including 0, the null space equation. So it's going to be 6 minus 3 times 2, which gives us 0 here. So we're multiplying the first row by 3, subtracting it off. So 12 minus 12, again a 0. 12 minus 9 gives us just 3, so that's a bit different. And then we have a 6 here. Interesting things are happening. And then there's a B3 minus 3 times B1. So again, we could do those two steps together because they're not interfering with each other. So we're starting to get a staircase structure. We would have said that the second pivot is missing. Actually, it's just in the third column. That's what was the sneakiness there. So let's try to use the same format. So it's going to be, now you can see what we're doing. We're just going to subtract the third row, the second row from the third row. But let's write it out properly because we're good people. It's 1 times row 3. Oh, so nice. Minus 3 over 3, right? Let me point out what this is. This is D1, D2. Pivot 2, which of course we would call, so let's call them divots. Divot 1 and divot 2. All right. I needed to I want to use a different color there. Yep. Now it's all fallen apart. My clever scheme that a monk forced upon me. So 3, 3 like this, that's good. Right? Oh, I need a big squiggle thing. Okay, good. Working through it. Must be able to do this. Okay, so the first row and the second row are the same. B1, and then 0, 0, 3, 6, and then fantastically, all zeros here. We've still got this same structure over here, so it's B2 minus B1. And now we're going to subtract this piece from this piece. So we have to concentrate a little bit. Right, so it's going to be B3 minus 3B1. Well, let me write it like this. Right, so there'll be a B3 minus 3B1 minus B2 minus B1. So I want to put, doesn't really matter about the order, so it's okay. We'll put B3, there's a minus B2, and then a minus 3B1 plus B1, so minus 2B1. Right? Good. Okay. So we know some things about this. We know that, actually, so I guess we should be able to say this, that, yeah, we can say this. So if this isn't 0, there's no solution because this last equation will just say 0 equals some number. All right, we're going to come back to that in a second. Oh, in the next piece. This is all set up for us now. We need to keep going. We're going to do some harder work here. We now have our pivots here and here. And we're going to use this, so this is the Gauss-Jordan approach, right? That use where we would just keep eliminating everything that we could. So at this point, let me just identify some things. So at this point, here's our staircase. I'm going to tell you that this is a pivot variable or pivot column. Let's say that. It's a pivot column. This is going to be a free column. Right? This is a pivot column. Because if you look down through the column, it's, or if we look across the rows, this is the first entry in the row. This is the, after we've done row reduction, first entry in the row. They will then correspond to pivot columns, and this will be free. And analogously, we'll say that x1 is a pivot variable, x2 is a free variable, x3 is a pivot variable, and x4 is a free variable. All right, well, let's get to that in a second, but we have to keep going. This is actually, this is u, x equals c, right? That's where we are. But, so we keep going. This is the new thing. As with, say, inverses. And we did it in a very early example, but as with inverses. So we're going to keep going, which is to say, I want to get rid of all the numbers in each pivot variable. So I can't get rid of this 4, right? There's nothing to get rid of it with. So that's going to stay. The pivots are fine. That's a pivot here. I can use it to get rid of this number. And if I do that, then there's no way I can really leverage anything here, because once I've sort of cleared this situation up, I can't mess with it anymore, because I'll start to put numbers back here. So hopefully some playing around with that will help you see that. I mean, I'll keep talking about it in different ways. But it's only the pivot columns that can be cleaned up. So the next piece will be, there's one thing we do, it's going to be row 1 prime, is we're changing row 1 and we're using row 2, right? So it's going to be the old row 1. And we use the same kind of thing. It's going to be 3 over 3. The pivot is 3 on the bottom. We're trying to get rid of a 3. And we're multiplying this by row 2. 3 over 3. So essentially we're subtracting row 2 from row 1. All right, good. I need my big tildery thing. It's just nervousness. I don't know what that is. Okay, so I'm subtracting row 2. So they're all zeros at the start. Actually, well, first of all, everything else is the same. So let's do that. B2 minus B1. 0, 0, 0 along the bottom. Very satisfying. B3 or B or as that was, minus B2 minus 2B1. Let me get rid of this thing. Matrices do have a lot of funny noises associated with them. So 2, 4, so we're going to subtract this row off. I'm trying to use a different color. Help me. So 2, 4, 3 minus 3 is, as is tradition, 0. 4 minus 6 is minus 2 biscuits. And then we're subtracting B1 from this thing. This B2 minus B1 from B1. So we end up with 2B1 minus B2. You can think about that a little bit. Good? Okay. Almost there. So just as we did for inverses, we divide through by the pivots, right? Last step. So this is a big thing that we'll keep using all the way through. This tells you an enormous amount about a matrix. And just as a sort of a spoiler, the row reduction for A and then its transpose gives you basically everything. Hugely important. Well, it's just giving away the secrets to the universe. So easy, free. Okay, divide through by pivots. As they say in Australia, the pivots. That's a whole other business. So that is going to be row 1 prime equals a half of row 1, and row 2 prime is a third of row 2. Squizzle. All right. 1, 2, 0, minus 1. And then we have a half here. We have 0, 0, 1, 2. Now I want to create this B thing. We won't always do that actually, right? We'll often not use this B piece on the side, but this is important. So this is important for understanding. So we're dividing through. Well, makes it hard to do. And we need a third here. B2 minus B1. B3 minus B2 minus 2B1. Yeah. Okay, just a vector on the side. So this, yeah, good. So this whole thing here, huge. This is equal to what we're going to call the reduced row echelon form of A. And so this is not in a lot of books or your textbook, the textbook that's associated with this course. I find that very useful to have a sort of a identifier there. So R is a very, very special matrix, right? It's an operator, really. Right, you take A, make R. I'm just going to do that. So this is the reduced row echelon form. This is full of riches form of A. Just saying that, goodness. And it's always like this, right? So there's going to be this, look at that, it looks like the identity matrix. And I'll come back to that later on. Big deal. So first 2 columns, so many weird things of the identity matrix. What? Well, you think about what we're trying to do. That's what has to happen, right? And then the others are messed up, right? They have all sorts of things in them potentially, but we have this shelf structure, so that would go on in general. All right. So so we've got that. I've told you what the pivot columns and the free columns are. I want to also, I guess I've said it, but I want to make it clear. Okay, so let's write down, right, big deals, big deal things. If you look at this, there's nothing more we can do, right? We can't reduce this any further. I'm given this particular process. Right, we've cleaned out all of those pivot columns. There's nothing we can do about this 2. There's no way we can mess with these guys because as soon as we do that, we'll start to introduce non-zeros back. It's the best we can do. So that's going to be point 1. So we can't reduce any further. Yeah, let's write all the good stuff down. So that's a big deal. And then 2. Okay, I'll say this. RA is unique, basically. For any A, I mean, you could do some row swaps, and but anyway, it's basically, yeah. Row swaps is still possible, right? We're doing the normal thing, so row swaps are still part of the plan. Right, so still the same idea. We do row swaps to make, move the structure around. We want zeros at the bottom of the row reduced form if they're going to appear. So sort of a new thing is that pivots may appear irregularly. That's just a word I wanted to say. Irregularly. It's the L's. The L's are really good. That's the business right there. One, right? So they could be like this. There's going to be some junk here, maybe. This is all zeros, zeros, right? This kind of thing, 1, 1, etc. Zeros stuff, and there are always zeros above the ones, right? They always look like they're part of the. Obviously, it's a terrible mess I've made, but they look like they're part of the identity matrix. Good. Good. The pivot, so that's to say pivot columns match identity matrix columns. We're always cleaning out everything above and below the pivot. Again, some monks told us to do it. Basically, we'll do anything the monk says. So they just look like they, you just got to trust them. Yeah, right. And we always divide, right, so we always divide through to get the ones. So I think we know this. Okay, so here's a big deal. And this is what will end this thing. So very big deal. Very, very big deal. Well, also let me maybe just, I didn't write this, so maybe write this, put that over there. I'm going to say, yeah, we say, right, we call the x's, the xi, right, that match up. You know what, I should call them j. The xj that match up with the pivot columns, the pivot variables, and the free become the free variables. So similarly, also a fun word, similarly, free columns match free variables. Okay, good. So in fact, for phasic, so the x1 and x3, so for phasic, x1 and x3 pivot variables. Yeah, it's really, it was going to matter. It's unbelievable. Yeah, yeah. And x2 and x4 are free, Belgian style. Okay, good. Which is waffles. Okay, so you call them the waffle variables. That will be good. What's going on there is that French fries were going to be called freedom fries because people didn't like French, but it's really Belgium that invented the fries. So, yeah. All right. So, so here's a very big deal. It's a definition. The number of pivot columns is called the rank. Wow. The number of pivot columns, right? So we can only find this after we've done this row reduction. Yep. Well, we know actually when we've got to this point, right? Before we've started to clean out the entries above the pivots, but still, pivot columns is equal to this. No, I'm going to change that color so it doesn't get messed up. So the number of pivot columns equals the rank of a matrix in number of pivot columns in R of A equals the rank of A. And we write this as R, little r. Okay, so the notation is the rank of A equals little r. So for phasic, it's two pivot columns. Okay, so for phasic, our loyal incredibly good at rhyming person. R equals 2. So these are the really basic things about it, right? So in fact, you would say M equals 3, N equals 4, R equals 2. This is a huge. And so what we'll get to, so clearly that should look like it's going to matter in some way with respect to solving Ax equals B. What you'll find, this is very nice, that in every matrix there is a R by R square matrix hiding inside it. So this is sort of a huge idea. These ideas keep getting bigger. Inside every matrix, doesn't matter what's matrix A, and let's say it's M by N, there is an invertible, right? So a nice, healthy, invertible R by R matrix. Does that look okay? So I want to make that a better R. R by R. Hopefully I don't need to say square. Right? It's invertible only. All right, I'll say R by R square matrix. Which is to say that you've got some weird matrix, but it might map a plane in 4 dimensions to a plane in 3 dimensions over here. And they'll go back. You can map them nicely. It might stretch things and so on, and right? But this is a big deal, and it takes a long time to get there. So I'll just let the excitement build for it. So that's this is a big setup, right? We've got our matrix Phasic that we're going to work on for a while. We've found its reduced row echelon form. These the B's here will matter in a little bit, but it was just good to work with them. But in general, you don't need to use that. You don't need to carry that everywhere. It's just if this is a understanding thing, a thinking thing. And we'll come back to Phasic later on. I've got a whole set of stuff there for Phasic. Vizini will appear, as will the man in black, right? Very important matrices. They're different sizes. Okay, so the next thing will be to take this is a big setup, to take this and find the much vaunted column space and null space of A, and in this case, of Phasic.